Lynn, are you on?
Yeah, Matt, can you hear me?
We can hear you just fine.
Can you see my screen?
Yes, we can.
Okay, great. Thanks, Matt. Well, good morning, everybody, or good afternoon, I should say. My name is Lynn LeBon. I'm a product manager here at Halliburton Drill Bits and Services. Today, I'm going to talk to you a little bit about our Cerebro in-bit sensing product line. I'll give you a general overview of the product family, its capabilities, and the breadth of applications that we have. And then later on, I'm going to touch on a specific example of some insights provided by our latest product that we released called Cerebro Force. Many of you are familiar with our Cerebro in-bit sensor. Cerebro measures motion, vibration, and downhole temperature, and has been in the market since late 2018. We recently publicly released our newest offering, which is called Cerebro Force. Cerebro Force has all the same measurement capabilities as Cerebro, but also adds in pressure and strain sensing, which enables us to measure downhole weight, torque, and bending directly at the bit. Since the original release of Cerebro, downhole force measurement has been one of the most frequently requested feature additions by our customers. So we're very pleased to be able to offer this now. From the measurements that we take with Cerebro, we have a wide variety of calculated outputs. And so, when we're looking to optimize a drilling application, the most crucial step is to ensure you're solving the correct problem to begin with. Traditional dull analysis coupled with rig surface data has gotten us a long way, but it has limitations. Our downhole measurements allow us to accurately detect and quantify all the major drilling dysfunctions that can inhibit performance. These include the classical dysfunctions such as vibration, whirl, and stick slip. But with the application of gyros and other sensors, we can see things such as bit wobble. We can use frequency spectrograms to now analyze the vibration frequencies that we're having downhole, and look at things like enhanced depth of cut and enhanced MSE, which are enhanced for having the actual measurement of the bit speed in those measurements. Since Cerebro Force can accurately measure weight, torque, and bending at the bit, I can tell you a lot about bit cutting efficiency, weight transfer, and motor performance. And of course, with those downhole sensors, we can calculate an MSE that eliminates all of the measurement uncertainty from wellbore friction along the length of the wellbore. Both Cerebro and Cerebro Force are fully integrated sensors offered by Halliburton in our drill bits and XR reamers. One of the distinguishing characteristics for our in-bit solution is that we have the capability to record all of our sensor channels at 1,000 hertz for the duration of the run. There's other technologies out there, but often they're limited to burst data. Continually logging at high resolution for the length of the run provides hundreds of measurements per revolution of the bit downhole. And with a high resolution data, we can zoom in on downhole events down to the millisecond, which I'm going to touch on a little bit later in my example. Both systems are compatible with all BHA types, including rotary steerables, mud motors, and conventional iron assemblies. It is standalone and it's memory only, so it also means you can run with any measurement while drilling system or none at all, if that were the case. It doesn't require any human interaction at the well site, which is obviously, especially today with COVID and all that, is a nice feature. And it automatically turns on once the drilling commences after the bit's been made up. We have a lot of unique analysis that we perform, as a drill bit product line, but when we're running a BHA with Sperry, we also have the ability to merge our Cerebro data inside of Insight software and create logs and other visualizations that integrate the Cerebro app bit data with the downhole measurements provided by Sperry. We currently offer Cerebro sensors in all major drill bit sizes. We can also place Cerebro in a small non-magnetic drilling sub. Customers are often interested in Cerebro quality measurements at various points of interest along the BHA to compare with the at-bit data. Common placements include, above the drilling motor or near a hole enlargement tool. And as I mentioned earlier, Cerebro Force was recently launched. The launch size is the 4.5 regular connections, so sizes between 7 and 7/8 up to 8 3/4 inch hole. And we're working to expand both smaller and larger connection sizes to get the full range of applications like we have with the original Cerebro. So look for some more information on that near the end of this year and the beginning of next. Just to look at our, experience, you know, exact numbers on Cerebro and its competing products are pretty difficult to come by since it's a sub-market of the drill bit market. So I know Mr. Hutchinson from Spears touched on that earlier today. If you're still with us, it would be fantastic to have some market data on in-bit sensing, and I hope that's something you guys can take a look at. So in the absence of having a report from a company like Spears, based upon our own market knowledge, we believe we're leading the industry in terms of the scale and scope of our adoption of in-bit sensing. We've launched Cerebro in Q4 2018, and we've amassed over 930 runs globally in 25 different countries. Most of the runs have been in North America, but we've had runs in deepwater Gulf of Mexico and Brazil, hard rock drilling in Mexico offshore, Norwegian continental shelf, mature fields in the Middle East, and so forth. And an important reason why we're able to do that is that we've been able to aggressively roll this out because every bit run is owned by the local drill bit design team, or our Ardaghi teams. We've built this capability organically within our existing drill bit technology organization. There's only a small handful of people, such as myself and a couple folks in technology, that work on Cerebro as their only full-time job. We think this is a very important distinction between other platforms and really allows us to intimately tie downhole data to drill bit design. To talk about some of the application and use cases, first and foremost, Cerebro's here and is employed as a drill bit optimization tool for our deployed technology team. It is an integral part of the design of the customer interface business model. And, as I touched on earlier, it allows us to have superior application intelligence, which targets our solution optimization process in the right areas. And then when a change is made, it allows us to validate the changes to the drill bit and performance as to see if it met our expectations, and then tease up nicely the next round of optimization. So Cerebro doesn't necessarily change what we do. It accelerates the process and improves our win rate at every single step in the process. Drill bit optimization is our primary aim, but there's always more applications beyond the drill bit itself. Data collected at the bit can tell you a lot about the BA chain events that take place, such as a motor stall or torsional vibration. It can also be a powerful tool to identify events that cause catastrophic damage, such as a type of damage that can occur while you're drilling out cement. And a third case is, of course, collaborative uses outside of Halliburton. In 2020, it's important to collaborate to get the maximum benefit of digital technologies and measurements. Many operators are eager to share data analysis and understanding. They also expect collaboration between their service providers to get the most value from all the services that they're paying for. So being open and willing to collaborate is important in this environment. And then there's other products that can be derived from in-bit data. We just heard from James at Fracture ID. They have a technology to extract pseudo logs of geomechanical properties from the exact same data we use to optimize drill bit design. And so, in US land this year, there's not going to be a lot of sonic logs done on all the wells drilled, but every single drill bit used to drill every foot of the well. And that's a tremendous opportunity for the industry. So I'm going to get into the second half of my presentation and kind of focus on an example. Because of the time allotted, I only really have time for one example, but I wanted to just mention that in the following session, Seth Anderley, our Permian drill bit technology manager, is going to present a multi-well case study that highlights some more capabilities of Cerebro Force. Gabe and Dustin, I know hopefully you're still with us. You had made some comments earlier in the start of the day that I think you'll find what Seth is going to present to be pretty interesting. So for my example today, I wanted to highlight a special capability that we have when we combine downhole force measurement, high-speed sensing, and placing it below a mud motor. And so to begin, I just kind of want to start with a problem statement. We're logging 72 million measurements per hour that we're drilling downhole. And so if you printed a post-run data set after a run, it'd be a book that's 8 million pages long. So the question is, how do you make sense of it all? And what's the workflow? And so the analogy that I would like to use is, it's kind of like having a 20-camera security system in a hotel. No one goes back and attempts to watch all 20 feeds of their camera at the end of the week and hope that they see something useful. generally there's going to be a trigger that prompts you to look at a specific moment in time. This could be a report from a guest or something an employee had seen, or a motion detector on your security system, and so forth. And so we employ a similar workflow with our downhole data. So, the first thing we're going to do is look at our initial information that we have. This includes the run summary report that Cerebro can generate automatically, along with reports from the drilling rig about performance. Any one of these initial reports can prompt us to do some more analytical work where we look at Cerebro data merged with the available rig data. This is typically at a 1 Hertz frequency so that the downhole data lines up with the rig data. This is a very good level of detail to examine trends or spot points of interest. From an analytical perspective, this is our workhorse level of data analysis. Many of the insights that we have can be gained at this level of detail. But occasionally there are prompts that want to make you look at a deeper look and look at the data in its native state. And I'm going to give you an example of that. And I know I'm running against my time, so I'll try to do it as quick as I can. So the question is, when a motor stall happens, why? And how can we use downhole sensing to potentially indicate to us why a stall has occurred? So I have some example data I wanted to show you. So we're looking at 40 seconds of downhole data at 1,000 Hertz. From top to bottom, we have bending channel, torque channel, gyro bit speed, and then finally the weight on bit channel on the bottom. We can see the bit speed drop to 0 here. This is the start of a stall event. We can immediately see the torque climb over the course of 5 seconds to its peak value. Also, during the portion where we see the torque rising up at the top, we have the motion on the bending channel, which is the winding up of the drill pipe after the stall. You can actually count the peaks and the bending reversals here. It happens to be 4 wraps. After that occurs, we're fully stalled, and you can see the bending channel flatline along with the torque. There's a time delay, before this stall is recognized and the driller picks up off bottom, at which point eventually the motor is relieved and it can begin to rotate again. So we're looking at 40 seconds of data. To better understand why this occurred, we're going to zoom in even further, and this is half a second of downhole data plotted. So we can see that drilling proceeds normally up until about this point. Then we see a change. We can see a change on the weight on bit channel trend here. After a short delay, we see the torque begin to respond. And so the important thing to note is the 20 millisecond delay between the torque and the weight on bit led first. And so as it continues to play out over the next 200 milliseconds, we can see weight on bit steadily rising and a downward trend in the RPM until we have the stall. So this would be indicative of a stall that occurs due to sudden application of weight on bit. And then a second example of a different type of stall is when you're drilling along with steady weight on bit, like we see here, and then you begin to sense a rise in the torque. And the torque rises until you start to see a response in the weight on bit, which correlates with the exact same amount of time when you have C0 on the bit speed channel. And then your bit has stalled. And in this type of a scenario, high frequency data indicates the stalling was due to a formation change, because there was not a change on weight on bit, but we saw a very sudden spike in the torque downhole that initiated a stall. So I'll close my presentation briefly to talk about what we see in the future. First and foremost, a couple trends to keep an eye on and things we want to focus on. As I mentioned, we're going to expand Cerebro Force into more sizes. Look for more information on this at the end of the year. The second is that Halliburton is going to continue to aggregate the learnings from individual runs and refine our bit models and incorporate them into our design software, iBits. This is already taking place. We're looking at the relationship of bit design features and their effects on dysfunctions and performance. And we're finding many cases where some of these relationships challenge conventional wisdom that we have on drill bit design. A third frontier is storing Cerebro data in large data lakes, so that all the Cerebro data can be queried on a massive scale. Today, our limit on the rollout of Cerebro is not the ability to crank out the widgets to get downhole. It's having the manpower to properly analyze all the data. And so these tools will help us in achieving an even greater scale with the rollout of the product. And lastly, at-bit force measurement was mentioned as a commonly requested feature addition. right alongside that is the need to have the information in real time. And this is a need both internally at Halliburton and as well for our customers. And we're continuing to develop technology in the space to make it possible to have some of this data in real time in the near future. So that'll be the end of my presentation for this afternoon. I hope you enjoyed learning a little bit about Cerebro. If you need more information, please don't hesitate to reach out to me by phone or email. You can check on halliburton.com/Cerebro to get some more information. And I will turn it over to Mitch at Altera for the next section, unless there's any questions.
Yeah, thanks, Lynn. Let's, for all presenters, I guess, for this one, let's hold our questions. After Mitch finishes, we'll come back and answer them accordingly. Anyways, I'll turn it over to Mitch. Let me